I deeply appreciate the honor of being invited to give this year's Sardar Patel Memorial Lectures. I wish to thank sincerely the organizers for giving me this opportunity to pay my humble tribute to the memory of one of the greatest statesmen that modern India has produced. The title of these lectures is The New Era of Science, in which naturally we are all interested, whether our direct interests lie in science or elsewhere. The recent outburst of cultural activities, the numerous seminars, conferences, and exhibitions organized in Delhi and elsewhere in connection with the Buddha Jayanti celebrations have tended to highlight one major trait that characterizes all living ancient civilizations like ours, namely the remarkable resilience that they have shown all through the ages and the capacity for absorbing and assimilating newer and widely different currents of thought. Otherwise, these civilizations would not have survived so long. We were, of course, aware of this trait previously, but the recent seminars have brought it to light rather prominently. The Sanskrit scholars have a felicitous way of expressing this resilience. The word Puranaha means literally the ancient ones, but the scholars, taking advantage of the elasticity so peculiar to the language, have taken the word to mean Purapi Navaha, that is more fresh than ever before, which again serves to emphasize the peculiar genius of our civilization to assimilate and integrate many different cultural currents. Realizing unity in diversity, to use a much used phrase, has luckily been one of our major virtues. This virtue, which is so eminently characteristic of our cultural life, has unfortunately not been so apparent in our political life. Indeed, at many stages in our long political history, this virtue has been conspicuously absent. Even in the golden age of Ashoka, to which we all refer with a certain pride, the integration of the country was predominantly cultural rather than political. Real integration, extending not only over the cultural but also over other fields, is of a more recent date. At any rate, its sturdy growth is recent, and it had to avoid the nurturing care with which Mahatma Gandhi and his distinguished colleagues cherished them. It's therefore not without significance that we fondly refer to him as the father of the nation. The accomplishment of this task of integration of the country on the political side was in a large measure that of Sardar Patel, whose anniversary we are commemorating today. There is a close analogy between the virtues involved in cultural integration and those needed for the cultivation and advancement of the pure sciences. And similarly, between those involved in political integration and in technology. In this context, it may be significant that in India we took to the pure sciences much more readily than to the applied sciences. With our great cultural and academic traditions and the new political awakening, one may confidently look forward to a bright scientific and technological future for the country. Now, the main purpose of science is to understand nature in all her varied aspects and learn to control nature and to use this mastery of nature for the good of mankind. I am aware that even the mere mention of control over nature brings immediately to one's mind its misuses too, some of them frightfully inhuman ones. Indeed, when I was thinking of a suitable title for these lectures, I thought of the atomic age as a suitable one. But for the reason just mentioned, I fought shy of using it. I know also that many people who are not quite sympathetic to science have asked the question, why then apply science at all if its results are liable to be so grossly misused? They would quote very eminent authorities too. The well-known toast for science is, "Here is to science, may it be of no use to anybody at any time." The great mathematician Gauss, who would rank with Archimedes and Newton as three of the greatest mathematicians the world has ever produced, is reported to have said that if mathematics may be regarded as the queen of the sciences, then the theory of numbers should be regarded as the queen of mathematics. And he proceeded to give the reason: because it is the least useful. But the reply to these critics would be this: the ideal of knowledge for its own sake is a very ancient one, at least as old as Plato. It's also a laudable one and has proved to be of immense value. This Platonic ideal has inspired creative thought over all the intervening centuries in many centers of learning. It expresses the natural yearning of the creative artist to be left alone without being bothered by interference from what he would regard as the Philistines. I may be permitted a digression here. As some of you may know, what are now called non-Euclidean geometries were developed about the middle of the last century by 2 or 3 independent groups of mathematicians. It's a typical example of a problem which had resisted the attack of very able mathematicians for more than 2000 years, and for which, very strangely, the solution was found almost simultaneously by 2 or 3 independent groups of workers. Gauss certainly had the solution, probably earlier, but questioned why he had not published the solution. He made the characteristic reply that he feared the outcry from the Boeotians. Boeotia is a province in Greece which has been reputed for its dullness. In the context, Gauss was obviously thinking of the Boeotians among the mathematicians themselves and not of the uninitiated multitude. I permitted myself this digression just to emphasize that when Gauss claimed for the theory of numbers the unique virtue of being the least useful, he was merely voicing forcibly the traditional distinction between the arts and the crafts, between knowledge for its own sake, that is, knowledge that is not usable, and which for that reason was regarded as highbrow knowledge, and knowledge which is applicable. It was a distinction nearly as marked as the distinction between gentlemen and players at the Lords. Intellectual aristocracy is not peculiar to any one country or climate. I would remind ourselves at this stage, lest we feel very superior, of a proverb which is probably Sancho Panza's, that wisdom may not be all ancient, nor is all folly outdated. While I am on the subject, of course, the subject of applicability of knowledge, not Sancho Panza, I may remark incidentally that is hardly any branch of mathematics, however abstruse, which is not applicable. At a conference of mathematicians nearly 25 years ago, the question was pointedly raised, probably in the context of Gauss's claim for the theory of numbers that it is the least usable, whether, for example, the theorem of partitioning of numbers found any practical application. Presumably, the questioner regarded it as the least likely of application among the results even in number theory. The answer was surprisingly affirmative and came from one of the scientists in the Bell telephone laboratories who had been applying it effectively for his work on the splicing of cables. There are 2 research papers on this subject in the Bell System Technical Journal, to which I may refer the reader if he is interested. I mentioned just now that there is hardly any branch of abstruse mathematics, of even abstruse mathematics, which is not ultimately applicable. In the same manner, almost any result in science which is applicable for the good of mankind can probably be equally effectively misused. Belligerency, as David Sarnoff remarked, is an attitude of mind and not a property of matter, and therefore does not concern science as such. The cure for misuses of science is to stop the misuses and not to stop all the uses of science. It would be like throwing out the baby along with the bath water. It would be blackmail, for example, might be a form of telling the truth, but we do not for this reason think the less of the virtue of truthfulness. I may add incidentally that the corresponding Sanskrit word satyam, so dear to Mahatma Gandhi, has always been regarded as excluding misuses. Satyam yatha drishta artham hitarupa vachanam is an old definition of the word. That is, the content should conform to the best of one's personal knowledge, and its expression such as would conduce to the good of humanity. It's unfortunate that one has to use the same respectable word science even when it is grossly misused. It reminds me of a well-known Tamil classic in which the author deplores that the cultured and the vandals have the same external animal appearance. Most of the sentiments expressed by the ancients about the control of the senses and of the temptations are applicable to the proper uses and the misuses of science. The ancient teachers insisted on strict disciplining and proving of character of the disciples before they ventured to impart any knowledge, particularly knowledge of profound import. Though it might imply monopoly of available knowledge and might as such be itself a misuse, the basic principle underlying it might be of value even today. Probably, I should say, particularly today. Rajaji, my very distinguished predecessor on this platform, you may remember he initiated the Sardar Patel Memorial Lectures last year, has a modern rendering of this safeguard. It was not in his Patel lectures, but elsewhere, when he was in one of his characteristic Jules Vernian moods. What we need for the purpose, according to him, is a gadget for monitoring the operations of the human mind. And the moment it recognizes the image of an evil thought fleeting across the field of view, the monitor would operate a relay that will automatically freeze all further thinking and immunize the brain. The wording is mine. To ask well is to know much is an old proverb. All our great epics start with someone asking such a question. Papracha is a hoary word. The demand made of our gadget is one such. It implies that it is in the minds of men that one should seek a solution. It is not a problem in the physical sciences, but one concerning the human mind. After attending in this hall some of the sessions of the UNESCO, one almost hears the words of the first paragraph of the declaration ringing in his ears, namely, since wars begin in the minds of men, it is in the minds of men that the defenses of peace must be constructed. Coming back to my main subject, I mentioned that the major objective of science is to understand nature. It immediately implies a certain faith, which, however, has since been wholly justified by our wide experience, that underlying the working of nature and the operation of all natural phenomena, there is a certain inherent order and conformity to certain invariable and fundamental physical laws. Nature, as Einstein remarked, may be profound, but she never cheats. That is, she plays the game strictly according to the rules. The rules, of course, are of her making, but she never changes the rules to suit the vicissitudes of the game. There are no exceptions to these rules. The main purpose of science is to discover these fundamental laws of nature, to unveil the ultimate patterns to which natural phenomena and all the events in nature conform. In this sense, the function of science is more one of unveiling rather than of creating. A preliminary to it, or an essential first step towards it, would be a detailed study of natural phenomena, either in the fields or in the laboratory under controlled conditions, in which the parameters that are likely to influence the phenomena, and which are usually many and complex, can be varied one at a time. The major incentive at this stage is one of curiosity, in which every new phenomenon presents features of interest, and the traveler manages incidentally to accumulate a large amount of new knowledge. In the wealth of detailed information that accrues in this process of voyaging, he may not see the wood for the trees, but each tree is a novel type which attracts him. He may find numerous empirical rules and many regularities in his data, but they do not yet piece together into a single coherent whole. This stage corresponds to what the great philosopher and educationist Professor Whitehead would regard as the stage of romance in the education of a child. The next stage is one of synthesis, of trying to find the pattern into which all the observational data can be fitted elegantly. This is the stage of accurate measurement and rigorous disciplining. Through measurement to knowledge is the motto of a famous laboratory which did much of the pioneering work on the properties of substances at very low temperatures. Because, after all, it is the precise quantitative fit of the different quantities that are related to one another that gives science that great security which it would not otherwise be able to attain. I mentioned just now the quantitative fit of physical entities that are related to one another. This relation is naturally expressed in the form of a simple mathematical formula, and the quantitative fit amounts to a precise verification of it. It immediately raises a fundamental question. Mathematics, as we all know, starts from certain fundamental axioms and builds on the basis of these a logical structure. Taking, for example, Euclid's elements, we do not know how much of the knowledge contained in the available books of Euclid are his own, and how much of it is a codification of the then available knowledge. Starting from the axioms, with which we are all so familiar, the logical sequence in which the different propositions follow in his book is presumably Euclid's own. Each proposition follows logically and inevitably from the propositions that have preceded them, and the latter in their turn are based ultimately on the axioms. Fontenelle compared mathematicians to lovers. Grant a mathematician the least principle, and he will draw from it a consequence which you must also grant him, and from this consequence another, until you find that you have conceded him all the 13 books of Euclid, or at least those of them that are happily left. A fundamental question that I referred to is this. It has been posed by many philosophers. I shall quote it in the form in which it has been raised by Einstein. How can it be that mathematics, being after all the product of human thought, independent of experience, is so admirably adapted to the objects of reality? Indeed, he goes much further and declares that the creative principle resides in mathematics. I am quoting him now. And in a certain sense, therefore, I hold it true that pure thought can grasp reality as the ancients dreamed. It's Einstein. In the context of the profound issue raised, you will appreciate my quoting Einstein on this issue rather than the lesser philosophers. After all, physics is natural philosophy and has been so designated for quite a long time. One can also appreciate the earlier reference to mathematics endowing the sciences a certain security which they would not be able to attain otherwise. It's a fundamental corollary to all mathematics that you cannot draw out from it more than you have put into it in the form of the axioms. In a sense, the cleverness of the mathematician lies in his smuggling into his axioms essentially all that he wishes to prove elaborately later on. It's like the magician producing the kerchiefs in large numbers. They have been there all the time, only we did not realize earlier. In this connection, the amazing appropriateness of mathematics for dealing with problems of reality can be traced ultimately to the reality of its axioms, which are after all products of human experience and therefore conform to nature. I do not propose to answer in detail the further question that would be raised immediately. How far the external world that we see is real, has an objective reality, or how far is it ultimately merely a product of human thought? The answer is that it is real in the same sense in which the axioms of geometry, which are the result of human experience with the external world, are real. But I shall not try to justify my answer. I would leave it to the metaphysician. It's really his province. Now, the supreme adaptability of mathematical formulae to natural phenomena naturally secures for mathematics a preeminent place in the explanation of natural phenomena. It is almost an article of faith among physicists that the ultimate pattern with which all observable data can be fitted is presumably a simple and elegant one. If so, the simple and elegant mathematical formulae should find repeated application in physics. This faith has been amply justified by experience. The partial differential equations are a striking example. I prefer to base my illustrations on physics since I am closer to this discipline than to the others, but the conclusions are typical and would apply to all other disciplines too. One has merely to turn over the pages of some of the classic treatises on physics, like Kelvin and Thomson's treatise on natural philosophy, or Maxwell's treatise on electricity and magnetism, or Lord Rayleigh's theory of sound, or Lamb's hydrodynamics, or Ruth's analytical mechanics, or Low's theory of elasticity. One will meet the same faces, the same veterans who have been through many an old campaign and have of course survived. Among them, the partial differential equations are the most familiar ones. Indeed, their ubiquity is so striking that Einstein was forced to remark that the partial differential equations first came to theoretical physics as a servant, but by degrees it became its master. Among the numerous publications of Eric Bell on mathematics are two entitled Mathematics, the Handmaid of the Sciences, and Mathematics, the Queen of the Sciences, respectively. I do not remember which of these two books appeared first, but as a physicist, I have no doubt in which capacity mathematics stays ultimately in physics, always as the queen. Hertz, speaking of the famous electromagnetic equations of Maxwell, remarks, one cannot escape the feeling that these mathematical formulae have an independent existence and an intelligence of their own, that they are wiser than we are, wiser even than their discoverers, that we get more out of them than we put into them. These are strong words indeed, but coming from one who first demonstrated in the laboratory the real existence of the electromagnetic waves that are merely lurking in Maxwell's equations, and who in that sense gave a real body to these equations, he is certainly entitled to speak, and he knows what he is talking about. And further, he is generally sparing of words. The prominent position of mathematics is even more strongly illustrated by the position in which physics found herself not so long ago. A few very young men, all in their 20s, all of them extremely competent theoretical physicists, gained such control over the progress of theoretical physics that the physics of their period was referred to adoringly as Knaben physique. Knaben means boys, that is physics created by boys. I remember the then secretary of the British Association telling me a story which was of great topical interest then. At a meeting of the British Association, Lord Rutherford was to give one of the evening lectures. Modern trends in physics was suggested to him as a suitable subject for the lecture. Rutherford replied in a light vein, "I can't make that the subject of a whole lecture. I can say it in 2 sentences. The theoretical physicists have all got their tails up, and it is up to us, the experimenters, to pull them down by their tails." Coming from one who not only had immense regard for the theoretical physicists, but also supplied most of the meat for theoretical physics, the remark of Lord Rutherford serves merely to emphasize the position physics found herself in. I am sure he was as proud of Knaben physique as the boys themselves. Thus, the second stage in the development of the sciences is one of synthesis or consolidation or integration, and the main objective is to find the appropriate mathematical pattern in which all the available data can be satisfactorily fitted. As in solving a crossword puzzle, when one happens to hit on the right solution, all the facts fall in their proper places so readily and effortlessly. It is indeed the most dependable criterion of the validity of a theory. I shall quote just one typical example from the work of Maxwell, and in the sublime words of Boltzmann, who compared this part of the work to a musical drama. The adjective sublime, which I used just now, is that of Planck. You may judge its appropriateness yourself. I am quoting now Boltzmann. At first, one developed majestically the variations of the velocities. Then from one side enter the equations of state. Then from the other, equations of motion in a central field. Ever higher sweeps the chaos of formulae. suddenly or heard the four words, put n equal to 5. The evil spirit V, the relative velocity of two molecules, vanishes, and the dominating figure in the bass is suddenly silent. That which had seemed insuperable being overcome as if by a magic stroke. There is no time to say why this or why that substitution was made. Who cannot sense this should lay the book aside, for Maxwell is no writer of program music who is obliged to set the explanation over the score. Result after result is given by the pliant formulae till, as unexpected climax, comes the heat equilibrium of a heavy gas. The curtain drops. The next stage in the progress of the sciences is that of generalization. The mathematical pattern that was found to fit all the observational data in the selected field is found to have a much wider significance and is equally well applicable to other fields too. Obviously, it is these two later stages that endow the sciences their essential unity. Otherwise, we shall have just a heap of uncorrelated and innumerable facts. They are just the building stones. The beautiful edifice that emerges ultimately is naturally so different from the heap of stones that went into them that one may now almost forget the stones. It is like what the ancients call wisdom, rising above the details of knowledge. I shall illustrate with a few striking examples, again from physics. Before Newton, there had been naturally enormous amount of observational data on the mechanics of bodies, particularly on the motions of the planets. When once Newton had formulated his well-known laws of motion and the law of gravitation, all these observational data get fused into these simple, compact laws. When required, one can obviously reproduce these data, that is, calculate back the data from these basic laws of mechanics. Indeed, the simplification of the whole field of mechanics was so dramatic, and the transformation was done apparently so effortlessly, that a very distinguished historian could refer to this in just 2 sentences, very different, of course, from Rutherford's 2 sentences which I quoted. Newton said, "Let there be light," and there was light. It looked that simple to the historian. The events that preceded the formulation of the theory of relativity are equally romantic. There were numerous experiments performed which in effect, though not always actually, were attempts at measuring the absolute motion of Earth through space. Surprisingly, as judged against the then available scientific background, all the experiments were a failure. They gave completely negative results. An ad hoc explanation was offered in each case for the failure. And when the defects were rectified and the experiments were redesigned, they still persisted in yielding just negative results, until finally Einstein made the simple postulate that we are probably trying to measure something which is not measurable at all, even in an idealized experiment in thought, in which human and instrumental imperfections have been completely eliminated. It may be one of those quantities which we have come to designate as unobservables in physics. Starting from this simple postulate, one can draw many logical conclusions, just as one builds up his geometry from the axioms. One gets an entirely new picture of the fundamental concepts like mass, inertia, and even of the velocity of propagation of light from the source to the observer. I shall select just one of them for special mention here, namely the equivalence of mass and energy and their interconvertibility, which have formed the basis of generation of power from nuclear fission and nuclear fusion. Just as Faraday's discovery of electromagnetic induction may be regarded as having initiated the electrical age, the recognition of the convertibility of matter into energy, which is sometimes referred to as the etherealization of matter, has sponsored the age of atomic energy. Thus, on one side, science is expanding rapidly into numerous new fields, and new knowledge is accruing at a rapidly increasing rate, which makes science more and more complicated. And on the other side, the consolidation and integration are also proceeding rapidly, making science simpler and more tractable. I shall speak about these two competing processes more in detail in my next lecture. I wish to spend the remaining few minutes in giving just one example in which these two competing processes are very well exemplified. It was realized several years ago that the nuclei of all atoms may be regarded as built up of two fundamental particles, namely the protons and the neutrons, both of which have nearly the same mass, but one of them is positively charged and the other is neutral. With the two in appropriate numbers, one can build the requisite total mass and the requisite total charge of any given nucleus. The question arises as to how these two types of particles could be held together so strongly as they are actually found to be. None of the known mechanisms could explain such a strong interaction between them. Following the analogy of interaction between charged particles, namely through the electromagnetic radiation field, which may also be regarded as being effected through the exchange of photons or particles of light between them, Yukawa found that if the interaction between the protons and the neutrons is due to such exchange, the new particles concerned in such an exchange should have a mass intermediate between the mass of the electron and of the proton. This intermediate particle has since been called the meson. A new particle answering to this description was later found, which was very gratifying. It was soon realized, however, that though this new particle had some of the requisite properties, it was not quite the one that was wanted. The right one has since been discovered too, but meanwhile, a large number of other particles too have appeared in the field. Thus, while on one side the explanation of the nuclear forces has been accomplished and the appropriate particle has been found, we find ourselves saddled with a number of new particles for which at present we have no place in our scheme of things. This is typical of the two processes that have been going on side by side all the time in physics, one tending to expand science and the other tending to consolidate and simplify science. As I said, I shall have more to say on these in my next lecture. Thank you.